So I would like to thank the organizers for inviting me to this high-level conference. And I would like also to thank Hubert for being there at Saclay, back from the US. So actually, I may be the person having known Hubert for the longest time here, since I met Hubert in the DEA, the physique quantique in École Normale, when I was teaching with a former colleague, Jacques Descloiseaux, in statistical mechanics. So Jacques Descloiseaux, Hubert, and myself, we share three things. The three of us were at the same school, preparatory school in La Flèche in the old days, which is, a military institution. And then we escaped our fate at École Polytechnique by going to the École Normale. And then we ended up at Saclay, and then the three of us very much liked polymers, as you may know, random paths in general. So I'm going to speak about random paths today. So I save a few anecdotes for later in the day, maybe. And so I'm going to speak about this joint work with Saksman, Saksman, from Helsinki, a mathematician, Michel Zinsmeister, also from Orléans, and also Dimitri Beliaev, who is at Oxford. So, I'm going to see. So I will just be, you don't need all the details, but I will just, for being specific, I'm going to speak about the whole plane Schramm-Loewner evolution first. So this is a mapping from the interior of the disk here, the unit disk, to the slit plane. And you have one point which is sent to infinity. You have a source term here, lambda t, which is sent to the tip of the path. And here you have the Schramm-Loewner evolution in the whole plane setting. So the famous Schramm idea was to use a Brownian source term here, lambda of t, which is the exponential of the simple Brown motion. So there are some boundary conditions at time, at infinite time. And if you take the k equals 0 case, which is a case where here lambda of t is equal to 1, you have simply the Kuiper function here, and which is actually a mapping from the interior of the unit disk to the plane slit by a half line. So, and of course, if you take a kappa less than, which is greater than 0, you are going to have a fractal curve, which is this version of the SLE. So I'm not going to use all of these details, but just for, just making things concrete. And there is something which is important here, that this map actually maps to, this is the unbounded version. It means that the cut here goes to infinity. And if you take an inversion, which is 1 over f of 1 over z, you bring back the interior of the, you bring the interior of the disk to the outside, so c minus d bar. So you have, so this map is the bounded exterior version from c minus d bar to the slit plane. And in this case, the red curve here, the curve k, if you wish, actually becomes the infinity is mapped to 0, so it becomes a bounded curve. So this is bounded, so hence the word unbounded for this case and bounded for the 1 over f of 1 over z. So, so integral mean spectrum here. So you take a Riemann map, such as the one we just discussed before, from D to C, and you define the integral means by an integration of the piece moment of the derivative on a circle close to the boundary. So if you wish, you integrate on a circle here, which is inside the disk and close to the boundary. The fact is, the derivative becomes wild when you approach the boundary. And so this kind of moment captures the singularities of the integral of the derivative. So if phi is random, like in the previous case, you can take expectations. So the simplest thing to do is just to take the expectation of the integral mean spectrum. And then you define exponents, which are in general defined as a lim sup of the ratio of the logs. But if the limit exists, then you will have that, the I, this integral mean spectrum, is going to diverge when your circle approaches the unit circle as some power of 1 minus of the distance to the boundary. So, and this beta sub phi, depending on the map of P, is called the integral mean spectrum. So actually, it's a tool of complex analysis. And actually, if you if this derivative, the modulus of the derivative here, once you do the map, is actually the harmonic measure of the transform segment. So this spectrum is linked with the integral mean spectrum. It's related to the multifractal spectrum of the harmonic measure on the boundary K of the image domain. The K is a red slit we saw before. So if you define for alpha greater than 1/2 epsilon E sub alpha as being the set of points Z on the boundary where the harmonic measure in a small disk of radius R. So you look at the content in harmonic measure, which is the probability that Brownian motion sent from infinity length there. So you are going to find this omega scaling at R to the alpha, and you ask for the Hausdorff dimension of the set of points where you have this harmonic measure. This is scaling of the harmonic measure. So f of alpha is the Hausdorff dimension of the set E sub alpha. And you go from beta to f by Legendre transform of this type. So you don't need the details, just to understand that from beta here, you are going to get f of alpha by the standard Legendre transform. So what about the complex case? So there is something else, which is if you raise the derivative to the power p, where p is now complex, then you are going to access not only to the harmonic measure, but at the decomposition of the boundary in terms of logarithmic spirals. So you are going to have the spectrum giving you the decomposition of your path in terms of harmonic measure and logarithmic spirals, which are, again, conformally invariant objects. So, and if phi is random, of course, you take the expectation, and then you will have another spectrum, this time depending on the complex variable p. I'm not going to go into the details of this for the SLE, even so we know it, actually. So for the SLE, for the standard SLE, say the bounded version, there were a number of results, and essentially you get, so if you take the average spectrum, which I mentioned before, of the bounded version, the one which was 1 over f of 1 over z, you are going to find a spectrum made of 3 phases, a tip phase, a bulk phase, and a linear part, so for large p. So it looks like, I'm going to come back in a minute, looks like this. You have a linear part, you have the bulk part here for a certain range of p, and then you have another spectrum, which is the tip spectrum for p negative. So I mentioned this was the average spectrum. I'm going a bit fast here because somehow I want to give you some results, but not all the details. And here, so that was the average spectrum, which was actually proven by Beliaev and Smirnov in 2005, published in 2009, and actually corrected by us in some work later, which I'm going to explain in a minute. But I want to mention then, if you want to do the version, since it's a random map, we have also for probabilities the question of what is true almost surely. And that was done for the tip by this team, Johansson, Wiklund, and Loewner, and also for the bulk case, by Gwynn, Miller, and Son, more recently, and actually that was actually very hard to get. You should know, they were able to do this only by using what is called imaginary geometry, which was this theory set up by Miller and Sheffield, which looks at the flow lines of the GFF, the Gaussian free field, which flow lines are related to SLEs, and using that technique, they were able to access the spectrum almost surely to find this formula. But of course, in average, you also find it, but with lighter techniques. People like Smirnov and Binder, for instance, tried to derive that almost surely and could not do it, since you have to use other mathematics. So that was the case for the bounded all-plane SLE. And what was the problem in the original proof of Beliaev and Smirnov? The fact is, so this is a linear part, this is a bulk part. And you see, if you look at the tip one, the one in red, you see it crosses here, and so it supersedes here the bulk spectrum, which is exactly why you have this curve here. So it means when p is very negative, you detect the singularities of the derivative which are close to the tip of the path. This is why you see it at p negative, of course. But what happened is there was another tip, because that was, again, the bounded version. So you have this infinite cut, you map it back by 1 over z, and you find a bounded curve which has 2 tips. So there was a second tip, which was the image from infinity, and that second tip had its own spectrum, the green one, given by this formula, which we discovered. And in fact, the fact is, the result was correct because the red part was superseding the green part. But if in your path you don't go around the first tip, then you are going to see the green one. And the fact, so you could say, well, this is just a fine detail, but the fact is, because of the existence of this phenomenon, the proof actually was not correct, because they had some positivity conditions which failed, and they did not see it because of this. So there was a mechanism in the proof itself which was detecting this. So anyway, all is well. So you have this spectrum, which I showed before, but this was for the bounded version. Now, if you look at the unbounded whole plane, the one I showed first, where you had this semi-infinite random curve, this one actually has also a phase transition for a larger p, or p naught, which is given by this formula, or whatever, where the spectrum itself transforms into Z form, which is quite different from the other ones, and related to some, phenomenon observed before. So it means that from Z curve, which was a result of Beliaev and Smirnov, corrected by us for the bounded case, actually you move to a phase transition, which is here. So it means you have this, you have the bulk, and then suddenly you have this spectrum which supersedes the other one for large p. So this is somehow the state of the art for this expected spectra. And I'm going to move to something which is called the universal integral mean spectrum, which corresponds to take the supremum over all Riemann maps, which are from the unit disk, which are injective this time, and bounded. So you saw one example, which was this spectrum we had from the exterior, which was bounded. So this is something which was BD here means for bounded, and B is the supremum. So there is a famous conjecture that is, really not known. It's not known if it is true at all, but there is a strong conjecture made by Kraetzer. So of course it's after other conjectures, where the universal spectrum could be, so it's the biggest beta you could have for all conformal maps which are injective and bounded. And so the conjecture is that it starts with a parabola for p less than 2, and then at p equal 2 it becomes linear. So it's something very simple. And there is another conjecture which is made by Binder in 2009, which is for the p complex, which I mentioned before, it's simply the same thing in modulus. So it's a simple curve like this, a parabola, and at p equal 2, the famous p equal 2 or minus 2, you go to linear part which is symmetrical here. Actually, there are parts of this which are proven for large positive p and large negative p. There are results in mathematics. So it's a wild conjecture. Nobody really knows whether it is true or not. This was for injective phi's and bounded ones. So the first case, the one I showed before, for the SLE, I showed you the bounded spectrum. So if you take that bounded spectrum for any kappa, you're going to find that it is indeed lower than this one. And so there is now the question of what happens if you unbound your map, meaning the slit becomes infinite. The slit I mentioned before, the red slit. In that case, you take, so that was the definition of the universal spectrum. Now you take B of P, which is a sup over all injective spectra. And in that case, you have a result by Makarov, which is not very difficult to follow, actually, which is that actually the supremum over all injective maps which are possibly unbounded is simply the max of the bounded one and 3p minus 1. So if you take the Kraetzer conjecture as a starting point, then you have this cut here, with this straight line, which is the supremum, which is very similar to the phenomenon we had before for the SLE, where I showed you. I'll come back in a minute. I showed you that you had this spectrum for the bounded case of the SLE, and then if you take it unbounded by the inverse map, you have this superseding. Okay, that was for the as a motivation. So maybe I went a bit fast, but essentially you have this Kraetzer conjecture, and I'm going to illustrate it with the zeta function. So something we looked at it more recently, actually before the starting of the pandemics, and now we are reconnecting the dots. And so you look at the zeta function. So I'm going to change a little bit the perspective. And instead of having integral mean spectra from the unit disk, I'm going to look at integral mean spectra along some lines, as you will see in a minute. But I take this zeta function, so it's defined, of course, for real of S as the usual Riemann sum, and it also can be written as a product over primes of 1 minus p minus s to the power minus 1. And then, of course, you have analytic continuation into the whole plane, except for one pole at z equal 1, z equal 1. So, of course, there is a famous Riemann conjecture, and be quiet. I'm not going to tell you the answer today, certainly not. So the zeros should be on the critical line, which is 1/2 plus a complex part. And of course, there is something which is actually a tool which is very important, which is actually a randomized version of the Riemann zeta function, which is the same formula is here, where you replace you add a noise which is the exponential of exponential 2 pi I theta p, where the theta p's are ID uniform random variables on 0, 1. And then actually it converges for the real of S greater than 1/2. But if you put yourself to the right of the critical axis, and if you go to the critical axis, then this object becomes a generalized function. So it becomes a distribution, not a function. And so the Harper model, so we are going to be interested in moments. And so I'm going to look at the moments of this zeta. So let's look at the log first. So you look at this log on the critical axis, and for a complex part which is high along the critical axis. This is where things become interesting, when you go up high along the critical axis. And so you put a high theta plus h. Theta is going to be uniform in this case between capital T and 2t, where t will be large. And then you are going to look at small variations with h between 0 and 1. And then you define, so you take the first term of the expansion of the log, and which is here. So this is the first term of the expansion of the log here. And you cut, because the problem with all of these problems, when you are on the critical axis, is that you have divergences. So you have to rigorize your sums. You will see several examples. So this is the first example, where you are going to rigorize by putting a cutoff on P, on the prime numbers. So, and then that was done by Harper some years ago. This xh sub t, h is here, and the theta actually are log correlated, a bit like the GFF. And you have, so essentially when you have this pi p minus I tau, where tau is this complex, this number here along the imaginary axis, with p prime, you replace this p minus I tau by exponential 2 pi I theta sub p. That's the idea somehow of this randomization. And actually, it's actually pointwise a good approximation of the zeta function when you go high along the axis. So that was the definition. So essentially, but your p 1/2 here comes from the fact that you are sitting exactly on the critical axis, right? And so this is an example of the log of minus the log of the modulus, where you take this large t, which was tau before, for large t, and h between 0 and 50, and this is the way this the real zeta function behaves. So which looks like a bit like chaotic indeed. So for the moments of the randomized Riemann zeta function, there were a lot of studies actually over the years. So many recent results were actually obtained for the moments, the maxima, and the relation to Gaussian multiplicative chaos. So I put a list here of names because there are a lot of papers actually. And so some are in physics, like this one, mixture of physics and mathematics, and the other ones here are actually mathematical papers. So what are the objects the people look at? And actually that's an old problem. In the 30s, people were already looking at the average of these kind of things. Over a large interval, they would take 0 to t. They would average the moment, the gamma moment of zeta on the critical axis. They would put a large t here, and they would integrate up to t. They would put, a tau, and they would, or h, they would integrate over h from 1 to t, and that takes the average. So people looked at that already in the 30s. But here, they look at something different. They look at moments on a finite interval on the critical line for large tau. So you move up. I will give you a picture in a minute. And for this, and of course, if you remember that we have this approximation of the log of zeta 1/2 plus I tau plus h, then you can look also at the moments. So here I put a normal capital M, here a script capital M for this expression, which is the approximation of the same quantity using the randomized version. Right? So this is a randomized version. The capital T here was, so this will be a kind of a random representation of that one. Of course, if you want to treat this one, you have to use specific tools too. So, but essentially there are some objects. This one, the randomized version again. So I'm going to put a picture here, which is better. So you are on the critical axis. This is T. This is 2T. T is large. You take 2 tau is in the middle. You have tau plus h. You integrate here along this segment. In this case, right? So you integrate on this small segment along the critical axis, and this is a zeta function you look at. If you take the random version, so it looks different because this was a log of zeta. So this is just the same expression in the random version. But the fact is, it no longer depends. It depends on t, but no longer on tau, since it is invariant. This one. It's supposed to capture what happens when you are far away on in the vertical direction. So again, this is a moment. The integral of the moment on a finite interval, and here this is the same thing, but in a random version. Even so, it looks different. And I put again the curly M stands for random, and the capital M for the Riemann zeta function. So what are the results in that field done already by mathematicians? So people look at the quenched free energy of the random version on the critical line. So again, this, and now they take the log of this expression. So you remember, it's quenched because you integrate this, and you take the log, and then you take the expectation of the log, which is usually more complicated than taking the average, of course. So you take this quenched version, and if you look at this free energy, between quotes, then there is a result by Arguin and Tai of 2017, where actually they show that the proper scale for these objects is log of t. You see here, the log of t. And so this is expectation of a log, so it's kind of like a log divided by log. This is going to give you exponents. And because here the log of t is actually the right scale. In the zeta function domain business, somehow, when you go high enough along the critical axis, the physical scale, say the geometrical scale, is log of t actually, and the spacing of the random the spacing of the zeros shrinks to 0 like 2 pi over log of t. So actually, you have this scaling, which is actually again a spectrum. So I call it f of gamma. I should have called it beta of gamma, because this is really a beta spectrum. And so it is given by this gamma square over 4, and then this linear part for gamma greater than 2. And you see it's very striking, because indeed it looks exactly like the Kraetzer formula for the supremum of the beta spectrum of the bounded Riemann maps in the plane. So, but that was for this kind of object, and then there is also another result, more complicated to get, by Arguin, Ouimet, and Radziwill, where they actually looked at the, so they looked at this expression again, this integral of zeta, the modulus of zeta, so for tau, and then they integrate over tau plus h, up to tau plus h, and now if they take a random tau in this interval t, capital T 2t, and then almost surely they are going to find this actually the scaling of the moment of the real zeta function, not the randomized one, is actually log of t times to the power f of gamma plus petit tau of 1. So that was a random version, and this is the same thing for the Riemann zeta function. So they do scale in the same way. So of course, what intrigued us was the fact that you would find here in this zeta function business exactly the Kraetzer conjecture. So we thought, gosh, if we could do, so this is not an integral mean spectrum because you integrate on a line of zero, or on the line of the zero. So we'd like to do something which approach the line and try to derive the same results on a different setting. So we looked at off-critical line moments. So now you move off the critical line. So you take S, the argument S of your Riemann zeta function like sigma plus I r, and then you look at moments which are of the same type, but now you are not at sigma equal 1/2, but you are at sigma at sigma greater than 1/2. So this was the setting before. You would integrate from here to here, and now we are going to move off. So we are going to do the same, but integrate from tau to tau plus h on slightly off the critical axis. So that defined a capital M sub tau, because you start from tau and depending on sigma here, an integral over h from 0 to 1. So now if you take the the random version, so you would like to study this. So you know that somehow the difficulty is that you have to go high enough in tau, so you have to move up with t, large t. Now you are going to, you approximate your zeta by zeta random. So you take the log of this, and you approximate again by the first term of the log of the Euler expansion, which was studied a lot. So instead of p 1/2 here, you put p to the sigma. If you do this, that sum converges much better. So you can now go up to infinity. You don't have. You remember before we put a cutoff at p smaller than large t. That was a way to represent the zeta function by a randomized version for large t. Here we change the setting. We integrate over all prime numbers, but we take the power is slightly bigger than 1/2, and then it converges. And again, the theta p's are the same as before. They are these ID uniform random variables on 0, 1. So this is written like 8x sub h, because h is here, of sigma, because sigma is here. And then instead of looking at this one, you look at that one, which is with a zeta being replaced by the random version of it, and then you call it capital U curly M sub sigma of gamma, so which is again this exponential of x sigma sub h dh. And and then you are going to look at the scaling of this. And so this is, so you again you take the quench free energy. So you take again the expectation of the log of m. Before in the SLE business was complicated because it was complicated enough in such a way that you had two type of spectra. You had the average spectrum, and then you had the almost sure spectrum, as I tried to explain. Here, if you put the log outside, it is easy to calculate. You are going to find the Kraetzer formulae. But now, what you want to do it in a quench way. So you put the log, and then you do the expectation. Because in the case of this Riemann zeta function, you can do things a bit. You can do things in the quench way. And so there is this result we had, which is if you take the limit of this free energy between quotes, which is the expectation of the log of the integral, this free energy divided by the log of the distance, the inverse distance, actually does scale to the same spectrum as we had before. So which is this time the Kraetzer spectrum. So it means that this f of gamma, before I called this p, right? And now it's called gamma. I'm sorry about that. But essentially, so gamma is like p before, and so the f of gamma is the Kraetzer integral mean spectrum of. So we got this for the moments of the derivative. So it means the derivative was the randomized zeta function. So it means the map itself is the primitive of that. So it means the map here, our candidate, is just the primitive of the random version of the zeta function. So you could say, well, this is great because you got one example of a conformal map which is, so of course here we integrated along, a blue line, remember, which was somehow the same thing integrating along within the interior of the circle before in the disk, but that's the same, of course, equivalent. And so the question is, what about the Kraetzer conjecture, which is, a wild but very well-known conjecture in complex analysis? So the question is, do we fit within the conditions of the oh, sorry, I just forgot about how do you prove this kind of result? So actually, we got two proofs via the prime number theorem and what is called second moment estimates. When you want to have this kind of results which are quenched in probability theory, you have to do what people call second moment estimates, or via the relationship of that random version of the zeta function to the Gaussian multiplicative chaos on the critical line. Because as I said before, the zeta random, when you move from sigma to sigma equal 1/2, I explained it was a generalized function. So actually, it is related to a Gaussian free field on the line. And so there is a version of the, actually, if you want, Liouville quantum gravity on this line, which you can use to derive this. And so the question now about the Quasar conjecture. So actually, it concerns univalent, called univalent, or injective bounded functions, as I mentioned before. So the question is, what about the univalence of our candidate, which was this integral? So actually, unfortunately, we have a negative result. If you look at phi, which is a primitive of our random zeta function, you take the critical line and you take a small square to the right of the critical line, which is touching the critical line. So which is this square here, 1/2 plus h along the sigma dimension, and 0h along the vertical. So you take this square, q, and there's this open square, and then almost surely phi is actually not injective on q. And to do that, I mean, you just need, there are ways to show that. You need to show that this is a necessary condition for univalence, and which is that should be bounded. And actually, we showed that the supremum of z factor times the second derivative of our phi, which is the integral of zeta random. So it means 5 seconds over phi prime here is simply zeta prime random over zeta of random. And since you have an explicit expression for zeta random here, you can show that supremum when sigma goes to 1/2 by positive values actually is unbounded. Yes, and I think that finishes my talk. So it means we do have a candidate for the Kraetzer conjecture, but it's not univalent. It's not injective, unfortunately. And this is simply because you have this randomness in your random zeta, and sometimes you have points which go very high, which shoot off. So you can't have this expression staying bounded. So almost surely you do go as high as possible. Okay, so this is time for concluding. I may have been a bit fast in the SLE's part, unfortunately, but this is time to wish to Hubert a very happy birthday. I'm happy to have known him for 38 years now, and continue the tradition, started with Descloiseaux here. And thank you.
Thank you very much for a very nice talk. So we have time for some questions.
So in complex analysis, there are some other results constraining how you can injectively map the unit disk onto the complex plane. So for example, Bieberbach's conjecture, is that of any use for your?
Bieberbach conjecture,
yes.
As you know, it's proven.
De Branche theorem.
Yes, so it's proven. So we did not try to prove it at all.
No, but is it useful having such constraints?
Well, it's another work we did some years before. We looked at these moments of the. We looked at the coefficients of the expansion of this whole plane SLE. So we looked at the average of the squared of this. We looked at the average of these coefficients, and to look at the relationship with the Bieberbach conjecture. So we studied this a while ago, yes. Yeah. But I don't think we no. we made a nice study of this whole plane SLE for in this setting for the linked with Bieber-Bach, but again, it's solved. So we're just checking things. So
okay. Well, in any case, you are right. We should call it the Branche's theorem because after what Bieber-Bach did to Schur, maybe.
But actually, as you may know, Loewner invented his Loewner equation. I mean, the Schramm-Loewner is the one with the random noise, but the one of Loewner was, of course, dates back from 23 or 27, I don't remember. And it was invented for proving Bieber-Bach conjecture for the third moment, for the third, third term, A3 of the expansion. So he invented the Loewner equation for that and proved it, actually.
Well, I wanted to say I was very thankful to Bertrand and Jacques Descloiseaux. They really gave me the taste of Saclay physics in a context where we were saturated from hearing about mean field theory and W bosons and all these kind of things. And that was really wonderful. And Bertrand was a wonderful teacher. He was extraordinarily annoying. He was constantly provoking you, always implying you wouldn't solve the problem, always implying he knew better. And I cannot tell you how motivating this was for a few of us. For me,
especially for Hubert.
For me, certainly, it worked beautifully. So that was fun. Thank you, Bertrand.
Well, thank you, Hubert. There was somebody else who came to Saclay in the same under the same conditions with Jean-Yves Littrot some years later, I guess.
So are there any further questions? And well, we're certainly looking forward to the further anecdotes you announced regarding Hubert's military career.
I have to invent some, yes.
Okay, but for now, let's thank Bertrand again for a very nice talk.